In this screencast, we're going to look at an example of a vector space, the set of functions defined on the entire real number line. This vector space is actually so crucial because you can describe radio waves, light waves, sound waves as functions, and we're going to actually be able to use this vector space, the set of functions defined on the real number line, to be able to show that lots of other different kinds of spaces are vector spaces or vector subspaces of this space. So first of all, we just need to remind ourselves there are 10 different axioms. We need to show that vector addition and scalar multiplication are closed, and then we need to show there are 4 properties related to addition and 4 related to matrix or to scalar multiplication in order to show that this vector space is actually a vector space. So first, we need to make sure we have a way of adding functions. And the way we add functions is, well, if I want to take a function f and I want to add a function g to it, well, functions are defined by what they do to a number x. So this is just put x into f, put x into g, and add them together. And notice this is a function. So the sum of 2 functions is, again, a function. We can also multiply. We can take a scalar, a number, and times it by a function. Well, what does that function do? Well, the idea is let's put x into the function f and then multiply by the scalar c. So just as some examples, if one function is 2x and another function is sine of x, the sum of those 2 functions is just 2x plus sine x. If I take the function sine of x and I want to multiply it by the number 7, then that's just 7 sine of x. In other words, it's really just function addition and multiplying by scalars, which is something we've been doing for a long time. Now we need to show it satisfies the 8 different addition and multiplication axioms. So the first one, we need to show associativity. We need to show that if I take f plus g and add h to it, I get the same thing as if I do f and then add to it g plus h. Well, both of these are defined by what they do to x. So if I put x into each, that's just f of x plus g of x. These are 2 real numbers. H of x is also a real number, and we already know that it doesn't matter where you put parentheses when you add real numbers together. So associativity is done. Commutativity, if you take f plus g, is that the same as g plus f? Well, and that's just it. F of x plus g of x is the same thing as g of x plus f of x, and that's just the commutativity of real numbers. The third axiom says there is a 0 function. Well, the 0 function is put in x, get out 0. That function satisfies, if I take 0 and I add it to any other function, I get g of x, which is the same thing as if I were to take g of x and add 0 to it. So we satisfy the third property that there is a 0 vector. The fourth property says if I start with a function, there is a way to create the inverse. Well, the inverse is negative f of x. So for example, up here, the inverse of 2x is negative 2x. The inverse of sine x is negative sine x. In other words, it's just simply multiplying by negative 1, and if I add those together, I get the 0 function. That completes the 4 axioms related to vector addition. We now move to scalar multiplication. The first axiom says that if I take a real number and I multiply it by the sum of 2 functions, it should be the same thing as the constant times the first function plus the constant times the second function. Well, these are just 2 real numbers. That's a real number, which means this is just distribution of real numbers. Similarly, if you take 2 scalars and multiply them by a function, you ought to get the same thing as c times the function plus d times the function. And again, this is just distribution of, we take 2 real numbers, times them by a function, which can be evaluated at each point giving a real number, and this is just, again, distribution. The third axiom says that I need to be able to take 2 constants, and if I multiply the constants together and then times them by a function, that ought to be the same thing as if I take a constant and multiply the constant d times the function, and then multiply by the constant c. Well, this is just associativity of multiplication of real numbers, and we've already got that down. The last one says if you take 1 and times it by a function, f of x, it should be the function you started with. And again, that seems to be like a regular property. All of these properties are things you've been using pretty much your whole life, ever since you learned about function notation. These functions show that all functions, the set of functions defined on the entire real number line, is a vector space. And this particular vector space is going to show up over and over again as an overriding vector space, which we'll use to get other vector spaces. That completes the screencast.